Hello, viewers. In today's session, we are going to discuss some important results related to adjoint of a matrix. And here we'll derive some important results. And the first one is if A is a non-singular matrix, then the inverse of adjoint of A is equal to adjoint of A inverse, right? Where A inverse represent the inverse of the square matrix A, right? And here we'll prove this result with the help of some important concepts from a matrix. The first one is inverse of a matrix, and the second one is the adjoint of the product of two matrices, right? So let us see how we can prove this result with the help of these concepts. So now let us quickly see the definition of non-singular matrix. So here A is given as a non-singular matrix. So a matrix A is said to be a non-singular matrix of order say n if the determinant of the matrix A is not equal to 0, right? So whenever the determinant of a square matrix A of order n is not equal to 0, or it is non-zero, then the matrix A is said to be a non-singular matrix, right? So let us denote A inverse as the inverse of the matrix A, right? So if the matrix A is non-singular matrix, then the inverse of the matrix A is said to exist, and we know that the inverse of a matrix A is given by adjoint of A divided by the determinant of matrix A. So now to prove this result, let us start with this important matrix equation, that is the product of A inverse and A is equal to I, right? Where A inverse is the inverse of matrix A, and here we have the matrix A, and the product of the inverse of the matrix A with the matrix A is equal to the identity matrix, that is I, right? So this is the first step in proving this result, right? So let us take the adjoint of both sides. So we can now write adjoint of A inverse A is equal to the adjoint of the identity matrix I, right? So we have A inverse multiplied with matrix A is equal to I, and taking the adjoint of both sides, we have adjoint of A inverse A is equal to adjoint of I. Now to simplify this term, let us make use of this important result, that is adjoint of say the product of two matrices P and Q is equal to the adjoint of matrix Q multiplied with adjoint of matrix P, right? So the adjoint of the product of two matrices P and Q is equal to the product of adjoint of Q and the adjoint of matrix P. So now here we can take this matrix that is A inverse as P, and this matrix A as Q, right? So now adjoint of the product of A inverse A can be written with the help of this result. So now this equation can be written as adjoint of A. So first we'll write adjoint of A multiplied with adjoint of A inverse, and the adjoint of the identity matrix is the identity matrix itself, right? So adjoint of I is equal to I, right? So now we have this equation. So now, if we closely look at this equation number 3, then we can see that the product of adjoint of A and adjoint of A inverse is equal to the identity matrix, right? And let us see equation number 1, right? So here, if we have a matrix A, then the product of the inverse of the matrix A with matrix A is equal to I. So if we compare these two equations, that is equation number 1 and equation number 3, then this adjoint of A is the inverse of adjoint of A inverse, right? Because the product of these two matrices is equal to I. So comparing equation 1 and 3, we can see that adjoint of the inverse of adjoint of A should be equal to adjoint of A inverse, right? And this is our desired result. So now let us take one more important result. So if A is a non-singular matrix, then the determinant of adjoint of A is equal to the determinant of matrix A raised to n minus 1, right? And this n is the order of the matrix A, right? So A is a square matrix of order n. So in order to prove this important result, let us start with an important result from adjoint, that is the matrix A. The product of matrix A with the adjoint of matrix A is equal to the product of the determinant of matrix A with the identity matrix of order n, right? So we'll start with this important result from adjoint of a matrix to prove this result. So here we are given that this matrix A is a non-singular matrix, right? So it implies that the determinant of matrix A is non-zero, that is, it is not equal to 0, right? And moreover, let us take the determinant of matrix A is equal to K, where K is some real number, right? So now we can write this equation 1 as the product of matrix A and the matrix that is adjoint of A is equal to K times the identity matrix of order n, right? So now we have this matrix equation. So let us take the determinant of both sides, right? So we have here the determinant of A times adjoint of A, and then here we have the determinant of K times the identity matrix, that is I. So now to solve this left hand side, let us make use of an important result from determinants. So if we have the product of two matrices and then we take the determinant and the matrices are P and Q, then we have the product of determinant A, that is determinant P and determinant Q, right? So using this result and applying this result to the left hand side, here we have A as P and the matrix Q as adjoint of A, right? So this is P and this is Q. So here we have first the determinant of A and then a determinant of adjoint of A, and to simplify the right hand side, will again make use of another important result from determinants, that is k times the determinant of k times some matrix, say x, is given by k raised to n times the determinant, that is determinant of matrix x, right, where x is some square matrix of order n. So here this n represents the order of matrix x, right. So here the identity matrix is of the order n, so we can take this matrix x as I, and so we can write here k raised to n, and then we have the determinant of the identity matrix I. So now this that is the determinant of matrix A can be replaced by k, and here we have the determinant of adjoint of A, and here we have k raised to n, and the determinant of the identity matrix is equal to 1. So here we have 1. So now we can write the determinant of adjoint of A, and we have k raised to n times 1 is k raised to n, and then we can take k in the denominator of k raised to n, and remember the matrix A is non-singular, that is the value of the determinant A is not equal to 0, so k is not equal to 0. So applying the laws of exponents here, we have k raised to n minus 1, right, and again replacing this k by determinant of A, so we have determinant of A raised to n minus 1, and this is our desired result. So from this important result, that is determinant of adjoint of A is equal to the determinant of matrix A raised to n minus 1, we can also derive some other important results, right. And here if we replace this matrix A by say adjoint of A, right. So here if we replace this matrix A by adjoint of A, then this result can be written as determinant of adjoint of A, right. And in the right hand side, we can now replace this A by adjoint of A, so we have the determinant of adjoint of A raised to n minus 1, right, and the determinant of adjoint of A is equal to the determinant of A raised to n minus 1, so we can now again replace this determinant of adjoint of A as the determinant of A raised to n minus 1, and then here we have this exponent, that is n minus 1, right. So now if we multiply these two numbers, then we have determinant of A raised to n minus 1 square, right. So we are using this result and replacing this matrix A by adjoint of A, we have another important result, that is determinant of adjoint of A is equal to the determinant of A raised to n minus 1 square. So now let us derive one more important result. So now again we'll start with this expression, that is the determinant of adjoint of A is equal to the determinant of A raised to n minus 1, where n is the order of the square matrix A, right. So let us replace this matrix A by say A inverse, right, and let us see what we get. So substituting A by A inverse, we have the determinant of adjoint of A inverse, right? And here we have the determinant of A inverse and raised to n minus 1, right? So here we have the determinant of adjoint of A inverse, that is equal to the determinant of A inverse raised to n minus 1. So now we know that the determinant of the inverse of A is equal to the reciprocal of the determinant of A, that is 1 over determinant of A. So substituting for determinant of A inverse as 1 over determinant of A, we have a 1 over determinant of A raised to n minus 1. So we have 1 raised to n minus 1 over determinant of A raised to n minus 1. So the numerator is now equal to 1. So we have simply 1 over determinant of A raised to n minus 1. So now we can take the denominator to the numerator. So we have the determinant of adjoint of A inverse is equal to the determinant of matrix A and minus n minus 1. So we can also write it as determinant of A and 1 minus n. So we have the determinant of adjoint of A inverse is equal to determinant of A raised to 1 minus n.